Welcome back to Algorithms and Uncertainty. Last time we already started talking about online convex optimization, and we'll continue today. So what was the general setting? The general setting was as follows. We have these capital T functions f1 through ft, which are unknown to us initially. Each of them maps from a set S, which is a convex set of d-dimensional real vectors to the real numbers, and each of these functions is convex, which we define this way. What was this? The function value at u is at least what we would get via the linear approximation using the tangent hyperplane at v. So in other words, these functions always stay above their tangent hyperplanes. Now, what was the question? We have to minimize these functions. But of course, there's the uncertainty, namely we do not know which functions these are. These are unknown initially, and what now happens is the following. In step T, first our algorithm chooses one point wt from the set S, and only then it gets to know the function ft it is supposed to be minimizing, because it is incurring a cost of ft of wt. As we've seen, this generalizes, for example, the expert setting, in which we would set S as the probability distributions over our D experts. And what we've seen as a general algorithm was the following. This followed the regularized leader algorithm, that in step T we choose this point wt so as to minimize what? We want to choose the point which has been the best so far. So we're in step T, we know these functions f1 through ft minus 1, and we want to figure out which of the points would have been the best so far. But as things can start jumping around, when we just choose this would have been the best point so far, this was the follow the leader algorithm, we regularize this by adding this r of wt, which has the idea of, well, keeping us away from very extreme values. We've seen this in one example last time, where without this regularization we were jumping from the left to the right endpoint of an interval, but adding the regularization we kept in the center of the interval. And this is the algorithm that we'd like to analyze today. How would we want to analyze this? What's the benchmark? What's the kind of result that we'd like to get? We'd like to bound its regret. And the regret is just the natural generalization of the regret in the expert setting. Namely, what's the cost that our algorithm incurs? And what is the cost of the best single point we can play throughout the sequence? So as before, we were talking about the best single expert. Now we're talking about the best single point in the set S. What is the cheapest point that we can have that we could use for the entire sequence? Not a point sequence where we choose a different point in each step, but it's the same point in every step. And the question is, how much worse is our algorithm's performance to the performance of this best single point? And today we will see how to generally design these regularizers and then analyze this follow the regularized leader so that we get a no regret algorithm, which means that for growing t, this regret term will grow sublinearly. And to get us started on this, we will first have to introduce some further assumptions. Namely, we will have to introduce some assumptions regarding these functions ft, because unfortunately they cannot be arbitrary, but their growth has to be bounded. We will assume that these functions ft fulfill a Lipschitz condition. Why are we assuming this? What does this mean? Well, what this means is that we are bounding their growth. And why do we need this? We need this kind of for the same reason that in the expert setting, we assume that the costs of the experts were between 0 and 1, or more generally speaking, between 0 and rho. This is exactly what we are kind of generalizing now by introducing this Lipschitz condition, which is effectively bounding the growth of the respective functions. So how do we do this formally? Let's consider an arbitrary norm on the set S, on the set of the points that we may choose from. What this means to have a norm, we'll see in just a second. For the time being, let's just think of this as we have in the set S, we have vectors, and each of these vectors has a length. And the length of this vector is defined by its norm. And now what we assume is we assume that for any 2 points, the function value at u minus the function value at v is no more than L times u minus v. And this L, this is just a global constant, so that we have the same for all u, v, and t. So what does this mean? It's actually nothing complicated. So far, these functions ft could be arbitrary, but now we are assuming that they're not arbitrary, because we assume that they have to fulfill this kind of a Lipschitz condition, that the function value that we have at u minus the function value that we have at v, so by how much does the function value at u differ from the one at v, this is bounded by some factor times the distance between u and v. Because the norm of u minus v, this is nothing but the distance of the 2 points u and v. But this does not necessarily have to be the Euclidean norm. It can be any norm. What could be such norms? Let's see some examples. We might have the L1, L2, L infinity norm, or more generally, the LP norm, where we would say that the norm of a vector v is nothing but the pth root of the sum of all its components to the power p. And let's see how what we could get in more detail for the expert setting. In the expert setting, what was the set S? The set S was the set of all vectors which are non-negative in all components and in which the components sum up to 1. And what were the functions ft like? The functions ft, those were nothing but these functions which are lit times vi. And this lit we were always assuming to be between 0 and 1 or between 0 and rho. So how can we bound this L for this kind of a function? This certainly depends on the norm that we're applying here. So for the L1 norm, for example, the norm of u minus v is nothing but the sum of the absolute values of ui minus vi. And this tells us, for this condition here, that we can now see that ft of u minus ft of v, how much is this? Let's plug in the definition of the respective function. So we'll get some lit times, and then we'll take ui minus vi, and this is clearly now upper bounded by rho times the norm of u minus v. And by that I mean the L1 norm. So we could choose L to be equal to rho. But we could also consider a different norm and do the same kind of bound. Namely, if we were considering the L2 norm, so the Euclidean norm, then the norm of u minus v is the square root of the sum of the squares of the components. And what we see here is that the L1 norm is always at most square root d times the L2 norm. This is just coming out of these definitions, just a very simple comparison, or effectively it is, this is the Cauchy-Schwarz inequality. So this is how you could bound the L1 norm by the L2 norm. And what does this tell us? If we wanted to use now the L2 norm rather than the L1 norm, we could now also try to get such a bound here, like this one. We could now also say that Vt of u minus Ft of u minus Ft of v, this will be, of course, at most rho times the norm of times the L1 norm of u minus v, and this is no more than square root d times rho times this in the L2 norm. So in this case, we could choose L to be the square root of d times rho. Now you might be asking, which of the norms should we choose? Should we choose the L1 norm? Should we choose the L2 norm? Well, it doesn't matter. We can use any norm that we like, but in this case now it seems, why shouldn't we use the L1 norm? Because this L is better than in the L2 norm. Yes, that's true, but there's now the other side, which we will be considering next, where the norm actually does matter, and then maybe the guarantee that you're getting is better for the L2 norm than it is for the L1 norm. And generally, all we're doing today doesn't actually care which norm you're using. So you may think of doing everything in the L1 norm, for that matter, but we're expressing this in such a general way that it could also be the L2 norm, it could be the L3 norm, it could be the L infinity norm. It doesn't even have to be such an LP norm, it can be any norm. But what we'll now do is we will assume some assumptions, we'll introduce some assumptions on the regularizer. And there we'll again see the norm showing up. And there, this is easier to fulfill for the L2 norm than for the L1 norm. The second assumption that we're now going to introduce concerns the regularizer. Namely, what was the role of this regularizer? The regularizer was supposed to move us away from these extreme points. So somehow the regularization has to be strong enough to guarantee this. And what we'll introduce as an assumption is that the regularizer is strongly convex. It's not only a convex function, but it is even a strongly convex function. How is this defined? Let sigma be a non-negative real. And then we say a differentiable function capital F, mapping from our set S to the reals, is sigma strongly convex if for all u and v from the set S, we have that capital F of u is at least capital F of v plus the dot product of the gradient of f at v and u minus v plus sigma over 2 times the norm of u minus v squared. And again, there's a norm showing up. It doesn't actually matter which norm it is, but it has to be the same as the one for which we defined this Lipschitz condition. Now what does this definition require from us? This looks a lot like convexity, but it is a little stronger than convexity. This is why we call it strongly convexity. Namely, what we now have is this further term here. First of all, you see that if sigma is equal to 0, then this is nothing but convexity. So every convex function is also 0 strongly convex. But maybe it is also sigma strongly convex for a sigma which is strictly greater than 0. When would this be the case, if this condition here is fulfilled? What does this mean? Well, recall that without this last part, we were saying the function stays above its tangent hyperplanes. Now we say it does not only stay above the tangent hyperplane, it even moves away from it. And let's see this maybe a little more graphically. What did we say a convex function looks like? Maybe this is a typical convex function. Why that? Because we could consider these tangents, maybe like this, and then the function was staying above this red line here at all times. This would also be fulfilled, for example, by the function which is this red line. So a linear or affine function, this would be nothing but its own tangent hyperplane. But what we now assume is that we actually move away from the tangent. Namely, this is what's expressed by this term. So what we have here is f of x, and this might be some x. Here, this might be our v. And now let's consider some u like this. Now what has to hold? It does not only have to hold that f of v, or I should maybe also say capital F here, because I'm now saying that this is a capital F, not to be confused with the small f's that we have for our as our input. So this is why I call this capital F. Now this, at this point u, this function capital F, this is not only above its tangent here, but it even is a little away from it, namely this much here. And we say that this has to be at least sigma over 2 times the norm of u minus v squared. So this here will be 0 if u is equal to v, but the further they are apart, the bigger this becomes, and so the further we should be away here. And our assumption will now be that our regularizer is sigma strongly convex for a sigma which is strictly positive. And depending now on how strongly it is convex, we will get a different regret guarantee. Maybe let's first see one example of a strongly convex function. And let's talk about our regularizer, one of our possible regularizers. Which possible regularizers have we seen so far? We saw this entropical regularizer, which was good for the, or which expressed exactly our multiplicative weights update. And then we also saw the Euclidean regularizer. And let's talk about the Euclidean regularizer because this is particularly easy to talk about. So how was this Euclidean regularizer defined? We set r of v equal to 1 over 2 eta times the sum of all components squared, or the square of each of these components. And I now claim that this is 1 over sigma, 1 over eta strongly convex. So what do we have to show to see this? We will have to see how is this condition here fulfilled. And let's first talk about the gradient of this regularizer, of this function. If we take the partial derivative in the ith component, how big is this? It is nothing but 1 over eta times vi. Yeah, sure, just take the derivative by vi. This is what you're getting here. And what does this now tell us? What's now the dot product of the gradient at v and u minus v? Well, This is of course nothing but the sum of all components. Take the partial derivative by vi and multiply this with ui minus vi. So this will be nothing but the sum of from 1 to d 1 over eta times vi times ui minus vi. And what does this give us? If we now take the dot product of the gradient at v and u minus v plus 1 over 2 eta times the norm of u minus v squared, and by that I mean the L2 norm, that's something that we can just calculate. The first thing we have already calculated. And what's this thing here? This is nothing but 1 over 2 eta, and then take the sum over all components. What we're getting is ui minus vi squared. Now, how big is this difference here? Let's see. What we're getting is nothing but vi times ui minus vi squared in this first part, and in the second part we're getting ui squared minus 2 times ui times vi plus vi squared. And this is nothing but 1 over 2 eta times, take the sum over all components, ui squared minus vi squared. And this is nothing but 1 over 2 eta. This is nothing but r of u minus r of v. And so, if we now read this from here to here, we see actually this condition that we were requiring is even fulfilled with equality, because we have r of u is at least or is even equal to r of v plus this here. And this is exactly what's here on the right hand side. Good. So this Euclidean regularization would be 1 over 2 eta strongly convex. The bigger the eta, the less strong its convexity is. Or in other words, the smaller the eta, the stronger the convexity will be. The slope will be more extreme for smaller values of eta. And I hope you recall that smaller values of eta correspond to a larger regularization, that the regularization plays a bigger role. And what we'll have to see is we'll have to balance out the amount of the regularization. Namely, what's very positive for us, if is if it's very strongly convex, because then things move away from the tangents very quickly, and this will turn out to be something very nice, very important for us. But at the same time, this might come at the cost of a very strong regularization. And a strong regularization, that's maybe not what we want, because maybe this means that we're not optimizing the functions anymore, but we're only optimizing the regularizations. Good. Now we've almost everything packed together to analyze the follow the regularized leader with these Lipschitz functions and with strongly convex regularizers. But before we get there, let's just make one more observation, namely that if we have a strongly convex regularizer, then also the functions that we are optimizing over, which was not only the regularizer, but the regularizer plus all the functions that we've seen so far, this will also be strongly convex. And this is the following observation. If R is sigma strongly convex, and F1, F2, and so on are convex, then R plus the sum of the F is sigma strongly convex. So this might be a misunderstanding. We are not assuming that the functions that we're optimizing over are strongly convex. They are just regular convex in the regular sense, in the usual sense. So there are at least 0 strongly convex. We only assume that our regularizer is sigma strongly convex, because then also the sum of R and the sum of the f of t, this will also be sigma strongly convex. Although these individual functions, they are only strongly convex themselves. So this is what the strong convexity of the regularizer buys us, that what we are then optimizing over in every single step of follow the regularized leader, this will be a strongly convex function. So let's now talk about follow the regularized leader with this strongly convex regularizer. We're now finally ready to analyze follow the regularized leader up to the point where we then get a real regret guarantee, for example, for the expert setting. And we'll, as I was saying, assume that these functions ft are Lipschitz, they fulfill our Lipschitz condition, and also that the regularizer is strongly convex. And based on this Lipschitz constant L and this sigma of the sigma strong convexity of our regularizer, we now will be getting a regret guarantee. Namely, what we will be showing is the following. If the regularizer R is sigma strongly convex, and each ft fulfills the Lipschitz condition with parameter L, the regret follow the regularized leader is bounded by take the maximum value that the regularizer can take in our set U minus what's the first value of the regularizer plus T times L squared over sigma. This L, this is the Lipschitz condition, and the sigma, this is the strong convexity. Before we move to the proof of this theorem, let's first see what this means for our expert setting. Namely, what could we do? We could, for example, use follow the regularized leader with an entropical regularization. We already know what's happening because we've already, or I've at least told you, that this is this multiplicative weights algorithm. But what we could also do is we could instead use this Euclidean regularization. This would also be a very reasonable algorithm. And we also know that this is a strongly convex regularizer. And indeed, this theorem will give us a regret guarantee for this other experts algorithm. Namely, let's put all the pieces together. When we're talking about the expert setting, let's talk about Euclidean regularization. What was this? R of V is 1 over 2 eta times the sum of the squares of the individual components. What's the maximum value that the regularizer can take? I will just tell you that this is 1 over 2 eta in this case. How can you see this? Well, the sum of the VI is at most 1. And now it's not difficult to see, but it's not super obvious that then also this sum here will never be more than 1 if the sum of the VI without the squares sum up to at most 1, or sum up to exactly 1. So this is where this is coming from. The maximum will be 0. The first value of the regularizer is at least 0. Good, now we have a bound for this and for this. What about our L and our sigma? Well, we've already talked about this today. For the L2 norm, we've already said we can choose the L to be square root of D times rho. Recall, this was what we were considering there, was first the L1 norm, for which we could bound the Lipschitz constant by only rho, and then we were considering the L2 norm, for which we got a worse Lipschitz constant, but at least square root of D times rho. And we've also talked about the sigma. This was what we did afterwards, and we showed that this Euclidean regularization is 1 over eta strongly convex with respect to the L2 norm. Both of this is with respect to the same norm. That's important. Although it doesn't actually matter which norm we're talking about. Good. So what's the regret guarantee that we're getting? The regret guarantee is 1 over 2 eta plus t times square root of d times rho, and this together we take the square of, divided by 1 over eta. So this is 1 over 2 eta plus t times d times rho squared times eta. And I hope you realize that this looks very similar to the kind of guarantee that we had also for the multiplicative weights algorithm. Now, depending on this eta, either this first term gets big or this second term gets big, and now we can choose the eta to balance the two off. And if we choose in particular now the eta so that these both get the same, then indeed we also will get a sublinear regret. So if we choose eta to be 1 over the square root of d2 times d times t, and then outside the square root we'll have a rho, then the regret will be at most square root of 2 times d times t, and outside the square root we have a rho. Which means that we have a no regret algorithm. The regret guarantee is a little worse than what we had for multiplicative weights. For multiplicative weights we had this t times log number of experts. Now it is just number of experts times t under the square root. And let's not talk about the rho and the factor 2 here. But at least we also have the square root t regret guarantee, which we know is optimal for this setting. And so this is an alternative no regret algorithm for the expert setting. And once again, how does the algorithm work? In each step, we choose the probability distribution over the experts, which minimizes the sum of the costs times the or the expected sum of the costs so far in this probability distribution plus the regularizer evaluated on this probability distribution. We'll see in a bit how you can also state this alternatively as a more natural algorithm. Cool. So all we want to do now is we want to prove this theorem. We want to show that the regret of follow the regularized leader is bounded by this term. How can we do this? Well, fortunately enough, we already have a regret bound for follow the regularized leader from last time. Last time we showed the following. We showed that the regret that follow the regularized leader has, after t steps, is at most the maximum of the regularizer minus the regularizer at the first step plus take the sum over all steps, and then we'll have ft of wt minus ft of wt plus 1. And now if we compare the two bounds, we actually see, well, the first part is the same. We only have to show that this here is bounded by this t times L squared over sigma. So what we'll be showing is the following. We will be showing that if the regularizer is sigma strongly convex, and Ft fulfills the Lipschitz condition, with parameter L, then, well, this thing here is bounded. And by how much should it be bounded? Yes, Ft of Wt minus Ft of Wt plus 1, this is at most L squared over sigma for all t. And if we have this, then we can only plug this in here. We'll get this t times this, and then this immediately implies this boundwidth we have in our theorem. Fantastic. So this is what we want to show. And the hope is that we can use this strong convexity to say that Ft and Wt and Wt plus 1 will always be close together. And this is exactly what we will show. We will show that due to the strong convexity, Wt and Wt plus 1 are close together. And because our function Ft fulfills the Lipschitz condition, also the function values will be close together. And this is the first lemma that we now show in order to show this other lemma. We will show that if we have a function mapping from S to R, which is sigma strongly convex, and we say that it should be differentiable, because we are assuming that all our functions here are always differentiable. And now we'll have the following. We let W be a point which minimizes this function f. Then what we have is that for all other points u, f of u minus f of w is at least sigma over 2 times the norm of u minus w squared. This is a crucial technical observation. Namely, we are using here these strongly convex functions, and as we already observed, in each step we are choosing the minimum of a sigma strongly convex function, because our regularizer was sigma strongly convex and we took this sum. This was the observation that we made earlier. Now, our point Wt that we're choosing in a step actually has exactly this form, that it minimizes this sigma strongly convex function. And now for every other point, u will have that the function value at u is at least the function value at w plus something. This is what we read here. If u is super close to w, there's not much that we're saying here. But if u and w are far apart, so u is any point, w was the point which minimized our function f. If u is very far apart from w, then also the function value at u is much bigger than the function value at w. Let's see why this is true. So how do we show this? Well, we use strong convexity, of course. And by strong convexity, we have that f of u minus f of w will be at least the gradient of f at w times u minus w plus sigma over 2 times u minus w, the norm squared. Now how big is this? We claim that this here is always non-negative. Why is this? This is exactly because we have a minimum at w. Well, first of all, if we had a local minimum just somewhere in the interior, then the gradient here would certainly be 0 in all components, so this would be exactly w. But more generally speaking, that if we suppose that the gradient at w and u minus w, that this dot product is bigger than 0, sorry, smaller than 0, then f is strictly decreasing at the point w in the direction of u, which means that w would not be a local minimum. So what will this look like? If this is our set S, then, well, if w is like this, it's super easy because the gradient will have to be 0 everywhere. Now what's more difficult is that if, for example, this is w, then the gradient is not necessarily 0. This is what you would have even if it is one-dimensional. Then if you're at the end of this interval, and there you have the minimum, the derivative will not necessarily be 0. But if you now take this as your other point u, and then you see, okay, what is happening on this line? And if this dot product here was now negative, then we would actually have a decreasing function, at least at the very beginning here, it would be decreasing. So this would be a contradiction to f being f having a local minimum at w. Good. So this is the key property of strongly convex functions that we will be using. And I think it's not really surprising. Given all we've seen about strongly convex functions, it is not surprising to see this property that if you move away from minimum, that then you can lower bound the function values depending on the distance that you've moved away. This exactly matches the picture that we've had earlier. And now we'll use this lemma to show this lemma, which was actually all we needed. In this lemma, we wanted to now say, okay, by how much do Wt and Wt plus 1 differ? Or more precisely, their function values, by how much do they differ? And to this end, we'll use this lemma, because both Wt and Wt plus 1, they are both minimizers of a certain function. And then we'll use Wt as this point u and Wt plus 1 as this point w, or vice versa. Let's see this in detail. Let ft of v be r of v plus the sum of all ft prime before time t. Now each of these ft is strongly convex, sigma strongly convex, because this R is. Now this Wt minimizes Ft. So by our lemma, what do we have? We have that Ft of Wt plus 1, this is not the minimizer of Ft, minus Ft of Wt, capital F I'm talking about here, this is the minimizer of this function. This is at least sigma over 2 times the norm of the difference of these vectors squared. And also, what do we know about the function ft plus 1, capital Ft plus 1? We know that there Wt is not the minimizer. Maybe it is if the 2 points are the same, but it should generally not be the minimizer. But Wt plus 1 is now the minimizer. And here on the right hand side we get the exact same difference. I now wrote it like this. Actually you could now also write Wt minus Wt plus 1, but that will be the same. The norm doesn't care. So now let's add up these two inequalities. We'll get that Ft plus 1 at Wt minus Ft at Wt minus Ft plus 1 at Wt plus 1 minus Ft at Wt plus 1. This is when we're adding these two inequalities. This is what we're getting on the left-hand side. We're getting this with a plus, and we're also getting this here with a plus, and then we're getting these two both with a minus. And this will be at least, okay, now we have the same on both right-hand sides, so we can just cancel this with the 2 in the denominator. Good. Now, how big will these differences be? Let's recall how the functions are defined. ft plus 1 and ft, how do they differ? Well, they both have the same here, except for one contains the small ft and the other does not. So this is why this is exactly small ft of wt plus 1. And same here, this is the same, and this is just small ft of wt. Good. So we have ft of wt minus ft of wt plus 1. This will be at least sigma times norm of their differences squared. Now, where do we want to go? What do we want to show? Actually, we want to see how does ft of wt and ft of wt plus 1, that this is bounded by this constant thing here. No, this is not actually what we want. And this is actually quite surprising because it here now says this is at least something. We want this to be at most something. But trust me, we'll get there. This here, this on the left-hand side, this is at most something. Namely, here it is, we can use the Lipschitz condition. The Lipschitz condition tells us, okay, the difference of the function values will be at most the Lipschitz constant times the norm of the differences. I now wrote it in this order. I could also write it in that order. This doesn't actually matter because now let's divide by this. We'll see that the norm of wt plus 1 minus wt is at most L over sigma. This is what's coming out of this inequality. And this tells us that ft of wt minus ft of wt plus 1, this is at most, well, it is at most L times the norm of the difference between the 2 points, and we know that this norm is at most L over sigma, so this is at most L squared over sigma. So this proof is actually super straightforward and at the same time super confusing, at least to me. Why is it confusing? Because there is this one magic, or there are these magic steps. Well, here so far there's nothing really happening, and then there are these magic steps here, at which we kind of get a lower bound on the difference between the two function values in terms of how far these 2 points are apart. And then again we say, okay, we can use the Lipschitz condition. And maybe the best way to phrase it is that if these two are really far apart, then we are getting a contradiction here at some point. And what is crucial here is that the definition of the strong convexity has this square inside. And this was also in this lemma that we were showing earlier. We have this square here. This square we do not have in our Lipschitz definition, in our Lipschitz condition, we do not have this square. And this is why here on the left-hand side we don't have the square, here on the right-hand side we do have the square. And this is why, well, we can effectively divide by this norm. By the way, if this is 0, then this condition, this inequality is true, of course, as well. So that's kosher here to do that. And then we use this Lipschitz condition once more. So generally, it is an easy, straightforward argument, but I think there's understanding the details here, well, this takes some time, or, well, just starting to not disagree with this argument. The general point that you should keep in mind is that we have this strongly convex function, and this causes us to not jump around too much, because, and this is maybe the biggest, or the core insight, that now it's only one of the functions in this sum here. So if you're adding or removing only one function here, that won't change everything, just because, well, there's so much else going on here. And this is only because we have this strong convexity. If we did not have the strong convexity, then, and this is what we exactly saw last time, then it can happen that suddenly the slope changes by just adding one function, and it changes so that we jump from this one endpoint of the interval to that other endpoint of the interval. But that is not happening with this regularization, with this strong convexity. Good. Now, let's see where we stand, and let's talk about entropical regularization again, because I think this is this is fantastic to see this. Namely, what is the bound that we're getting from this theorem? If we now apply entropical regularization, here we were applying Euclidean regularization. Now let's talk about entropical regularization. This was the multiplicative weights algorithm. Namely, what you will have is now that this RW is 1 over eta times the sum over all components Wi times ln Wi. Our set S is still the points with d dimensions in which all components are non-negative, and in which the components sum up to 1. Now, this R here, you can show to be 1 over sigma 1 over eta strongly convex with respect to the L1 norm. And what else do we have? We can set L equal to rho for the L1 norm, and we would have that the regularizer is now somewhere between minus ln(d) over eta and 0. So what's the regret bound? The regret is the maximum value that the regularizer can take minus the first value that the regularizer takes plus t times. And then we had our Lipschitz constant squared divided by the strong convexity parameter, which is 1 over eta. So what we're getting here is ln(d) over eta plus rho plus eta times t times rho squared. And with eta being equal to 1 over rho times square root of ln(d) over t, this regret bound will be 2 times rho times square root of t times ln(d). And that's actually amazing because it tells us that we're getting the exact same guarantee by now this much more general analysis that we've derived before. Before we've seen this guarantee via analysis for only this very specific multiplicative weights algorithm, and you can show that this algorithm here is equivalent to the multiplicative weights algorithm. And not only is it that, the analysis that we now have for this more general algorithm instantiated on this particular setting here gives us the exact same guarantee, which by the way is optimal. Good. So I hope you're now convinced that this follow the regularized leader is a super good algorithm to know because it gives us no regret algorithms, not only for the expert setting but also for many other settings. Well, sometimes you'll have to be careful that your Lipschitz condition is, for example, fulfilled, that you have this strong convexity, but generally in almost every online convex optimization setting you can now derive in a good no regret algorithm. I've now said multiple times that this follow the regularized leader in the expert setting with entropical regularization is exactly equivalent to the multiplicative weights algorithm. And this is only one case of an equivalence between follow the regularized leader and other algorithms. Let's talk about another algorithm that we've seen, which was in this expert setting. We also saw the algorithm using Euclidean regularization. And let me give you an idea of what this algorithm is equivalent to. I'm not going to the exact details here, or I'm only giving you the easiest of all possible arguments so that you see that you get an idea of what you can do much more generally here. Namely, if we have S to be all d-dimensional real vectors and the regularizer as our Euclidean regularization, and so this is Euclidean regularization, and I want these functions f to be linear. Then what does our algorithm tell us to do? We choose WT so as to minimize the sum of all points so far, or the sum over all rounds so far, and then this ft of w, which is nothing but lit prime times wi plus 1 over 2 eta times wi squared. This is, by the way, what we called capital Ft earlier. Now what if you take the partial derivative by wi? What you'll see is that, okay, you get all these. Here you're always getting the ith component, and then in the second part you're getting only 1 over eta times wi. And now wt is chosen so that this thing here, or that this function is minimized, which means that this will be 0. So we have that this will be 0. And this means that wit is nothing but minus eta times the sum of the lit prime. Meaning that the entire vector w is nothing but minus eta times the sum of these vectors, or what I can also write this recursively. I can say that this is the previous vector minus eta times the new vector. Times the vector that I got in the last step. And this is a rule that you may have seen before because it is exactly the gradient descent rule. This is an algorithm called gradient descent, and this is equivalent to this follow the regularized leader with Euclidean regularization. I should say that this is online gradient descent because I'm choosing this once I'm doing this update exactly based on the one piece of information that I got in the previous round. And equivalences don't stop here. Actually, for every function, you can do something like this. There are many details that you'll have to be considering, but eventually what you can see is that follow the regularized leader is equivalent to a generalization of this online gradient descent, which is called online mirror descent. Then these update steps get a little more complicated because what you'll do is you'll first mirror to some other space. There you'll do a gradient descent step and then you go back. But this is actually the only difference. So online gradient descent is just one particularly simple example of this online mirror descent, and generally every follow the regularized leader you can understand as some implementation of this mirror descent. Which, by the way, tells us also how to efficiently implement the algorithm, because so far we were only saying, okay, take something that minimizes this and that, but how are we even supposed to find this? Here, this suddenly is super clear what we should do, because it is just some pretty obvious update rule. Cool. One more thing to say is that here this is only so easy because we don't have any constraints. I was saying that this set S should be all d-dimensional vectors. If you introduce some constraints, then things become more complicated, but effectively the general idea stays the same. So, I hope you see that there is so much more to learn about online convex optimization, and we've barely scratched the surface of this. But still, I hope that this was inspiring to you to see that we can go far beyond this expert setting, and there's a big world outside in which, well, what we've seen, all this regret learning stuff, actually has much more general perspectives and has a very different interpretation, can be generalized to all kinds of settings, and there's so much more to understand also for myself, and not only for all of us, but also for the general scientific community. I think this is a super exciting topic, and there's so much more that you can learn if you're only interested. This is it for today. Please do reach out to me if you have any questions. And see you next time. Stay safe. Bye.